Hello class, this is Mrs. Ayodeji with today's video on sections 1.4 and 1.5, formulas for linear functions and geometric properties of linear functions. As you're watching the video, don't forget to write down important vocabulary, formulas, equations, examples. Feel free to pause or rewind the video as often as you need to get a clear understanding of what is occurring. And at the conclusion of watching the video, write a brief summary of what occurred in the video and submit that summary via the as well as a top question via the online whisk. All right, let's begin. Today's video is going to be mostly a review of a lot of topics from middle school math, but we're just making sure everyone has a clear understanding of what each of these topics are. The first topic is formulas for linear functions. You are going to be expected to be able to find a formula for a linear for a linear function from different formats, from numerical formats, which is data, from graphs, from just word problems to be able to find a formula. And so we're going to go over some quick examples of doing that for each one of them. So if I have a set of data like this, and I want to form a linear function to represent this data, first I must make sure that this data represents something that has a constant rate of change. Okay, in this case, we have the velocity of a grapefruit t seconds after being thrown into the air. And so what we do is let's take a look at what's going on from time 1 to time 2. The change in the rate of change in velocity with respect to time would be basically the difference between 16 seconds and 48 seconds. So you see here, 16 feet per second versus 48 feet per second. And then of course the change in time is just 2 seconds minus 1 second, we get negative 32. Let's see if that happens if we take a look at another pair from time 2 to time 3. So in this case, we're looking at the velocity of negative 16 seconds and 16 seconds, and the difference between those two is actually negative 32, and of course the change in time is 1 second as well, and so we still also get negative 32. So if we were to take a look at from 3 to 4, do the exact same process, and this time with respect to 48 seconds and negative 16 seconds, we still get a rate of change with respect to 1 second of time of negative 32. So this is a linear relationship. And in order to come up with an equation to represent the linear relationship, we must use y is equal to b plus mx, or y is equal to mx plus b. We know that m is the same as the rate of change, which is negative 32, which is constant, as we saw in the other ones. And so we just basically plug this in, but we're no longer using y and x, we're using v and t. That's very important. You make sure that your variables represent the situation. And so since m is negative 32, we have something that looks like this, and to solve for b, we just pick any one of the pairs. I just picked the velocity of 48 feet per second when time is 1 and plugged it into the expression, i.e. substitute, and I got that b was equal to 80. So now I have an expression, a function that relates the relationship between velocity and time in that graph. Okay, and that's that formula. If I want to be able to find a formula for a linear function from the graph, I would do basically the same thing. I would find the rate of change, and then I would use a point from the graph to figure out the y-intercept. It's easier if when we have a graph instead of a table, because we can identify by looking whether or not the function is linear. We don't have to do all the tests to see. We can take a look and see, is it a straight line? Then it is linear, and both of these are linear. And so what we're going to do is we're going to use the 2 points, exact points that they've given us, to compute this. Okay, so this is an oxygen consumption versus heart rate graph, and these are the 2 points that they've given us for line A. And so we just basically do rate of change with these 2 points. and we get that the rate of change is 0.01. We don't need to do several other points because number one, we don't have several other points, but number two, we already know the graph is a line. And so we are going to have linear relationships. So now we can just pick one of those points. It doesn't matter which one, the 100, 1 or the 160, 1.6, and substitute it into this expression. And we're going to end up with b being equal to 0, and this is our expression, which is consistent with this graph. Okay. Now, what if I don't have a table or graph and just have a verbal description? If I just have a word problem, how do I know, number one, is it linear, and how do I come up with the equation? That's super easy. Let's take a look at an example. We have $24 to spend on soda and chips for a party. A 6-pack of soda costs $3, and a bag of chips costs $2. The number of 6-packs we can afford is Y. So Y represents the number of 6-packs of soda, and then X represents the number of bags of chips we decide to buy. Okay, and so without even thinking about linear expressions, just in common sense, if you have $24 to spend on soda and chips, and Y represents the number of 6-packs of soda and X represents the bags of chips, then basically the equation relating X and Y can be found by adding up the amount spent on chips with the amount spent on soda and making sure it equals 24. Well, since X bags of chips at $2 per bag, then the amount spent on chips is 2X. And since for Y, 6-packs of soda at $3 per 6-pack, then the amount spent on soda is 3Y. So now I can replace this with this, and I can replace the amount spent on soda with this. And so we end up with an expression 2x plus 3y is equal to 24. And this is a form of a linear equation, and it's just a special form. It's not the slope-intercept form. It's called the standard form. And it looks like either ax plus by equals c or ax plus by minus c is equal to 0. Okay. If I want to change it back to a slope-intercept form that you're used to, y equals mx plus b, I basically isolate y, so subtract 2x from both sides, and then divide both sides by 3. And so these represent the exact same linear relationships, except one is in standard form and this one is in slope-intercept form. Okay. So I know some of you may be asking, what other forms are there of graphs, of linear functions? And there are several forms. We're already familiar with the slope-intercept form. But there's another very important one in calculus called the point-slope form, which we can derive basically based off the rate of change formula. But here, the variables are y naught, m, and x naught. Of course, m represents the slope, but x naught and y naught represent a point on the line, and it's any point on the line that will work. And then, of course, the standard form, the one we just talked about, is when x's and y terms are on the same side of the equation, and that's where a, b, and c are constant. So, unfortunately, a, b, and c don't directly tell you what the slope or y-intercept, well, c could tell you where the y-intercept is, but they don't directly tell you where the y-intercept is, okay? And so in this case, when back to the previous example with the oxygen consumption, we had the slope was 0.01, and we had 2 points. If we use the slope-intercept form for this particular point, we can just plug in our x and our y, and we can have a point-slope form. This is sufficient. This represents a point-slope form. This also represents a point-slope form of the exact same equation, and this simplifies to either a point-slope form or a slope-intercept form, but really it simplifies to a slope-intercept form because the intercept is 0. Okay, and no matter which point we use, in this example we use 1 and 100, we can use 1 and 160. and plug them in. This also represents a point slope form of the exact same relationship. And when I simplify this by isolating y, I get the same final answer. So they represent the exact same situation, even though they use two different sets of points. Okay? All right, so that's enough for that chapter. Section. Let's go to 1.5, geometric properties of linear functions. So remember, a linear function of the most popular form is represented by y equals b plus mx. And the parameters of this function are things that can change. And the parameters here are b and m. And we can use these to compare them to other linear functions. So let's take a look at this example. Oh, sorry. So the y-intercept b tells us where the line crosses the y-axis. And if the slope is positive, then the line climbs from left to right. And if the slope is negative, then the line falls from left to right. But also the slope tells us how fast the line is climbing. This is a steeper line than this, which means that this line will have a larger slope than this line. Okay, so the larger the magnitude or the size of m, the steeper the graph. Okay, so when we talk about the steepness of a graph, it doesn't matter if the line is falling or rising. The steepness is based off the size of the magnitude, the size of the slope. Okay, so let's take a look at three different linear equations. And they're in terms of t for time and p, I believe, for population. And without even graphing, I can tell you that these three situations, I can give you some comparisons. First of all, if we take a look at the starting values, i.e. the y-intercept, in each of them we see that the function that has the equation that has the largest starting value is b, which means that it's going to appear higher on the graph when x is equal to 0. Okay, so it's going to appear higher, and the lowest one is a. It's going to appear lower. And then when we take a look at the slope, i.e. constant rate of change, for each of them, we see that one is positive, two are positive, and one is negative. But so that means that this one is falling, and then this one, these two are increasing. But if we look at the magnitude, this is the larger number, so this will be the steeper line. This is the smaller number in magnitude, 300 is smaller than 60, so then this will be the less steep line. And when you take a look at the actual graph, we can see that it supports what we were saying earlier, okay? That we have the higher, this is the higher on the y-axis, this is the lowest one on the y-axis, one is falling, but the steepest one is A, okay? And so that's what you should be able to do with any set of equations without graphing, and be able to compare them based off their parameters, slope and starting value. So let's take a look at some special lines. We've been talking about them in the previous class, but now we get a chance to actually take a deeper look at them. So we know slope is change in y, change in x, but what if the change in y is 0, or what if the change in x is 0? What kind of graph will that look like? Well, if the change in y is 0, that means that no matter which two points you pick, the y value difference is going to be 0, which means the y values are going to be the same. And that looks like a horizontal line. The y values are always going to be the same. And if where the change of x is 0, that means no matter which 2 points you pick on the line, the x values are always going to be 0, the same, not 0. The difference is always going to be 0. And so that's going to cause a vertical line. So in this case of the horizontal line, the y values are always 4, but the x values, it doesn't matter. The x value can be anything and it'll still be on the line as long as the y value is 4. So the equation of this line would be y is equal to 4. Okay, and then over here, we have here that no matter what the y values are, the x values are equal to the same value, which is also 4. So this vertical line has an equation of x is always going to be equal to 4. Okay, And that's when you have an undefined slope as well. Okay? Slope of parallel and perpendicular lines. Again, you guys are familiar with this. You should know that the slope of parallel lines, they have the same slope, they have the same slant. And the slope of perpendicular lines are not the same. They have opposite signs and their slopes are reciprocals of each other. So basically, we can describe it using these two relationships. If the lines are parallel, M1 is equal to M2. If the lines are not parallel, but they're perpendicular, then M1 is equal to the opposite sign of M2, and you divide, take the reciprocal of M2. Okay. Now, if the lines intersect, that means that their slopes are not the same, but that doesn't necessarily mean that their slopes are perpendicular. So lines that intersect have different slopes, but that doesn't necessarily mean they're perpendicular. And here are examples of such special types of vertical and horizontal lines that are parallel and, of course, perpendicular. If everybody want to know why do the perpendicular lines have slopes that are negative reciprocals of each other, I have a lovely graphic here. Here's one line, and the slope of this line is b over a for these 2 points that we pick. What if I basically rotate a 90 degrees and rotate b? And so now we have this situation. Well, they're also going to be the change in y and change in x of another line. And that other line is line 2. And so the slope of this line would be negative a over b, which is the same thing as the negative reciprocal of M1. Okay, and that's it. So I hope you enjoyed this review, and I'll see you in class.